Okay, in my last video, I kind of briefly explained a little bit about how the YUPANA works in a 40 base system. You can also use it in a 10 base system, and I'll go over that real quick. If you use it according to 10 base, you can add and subtract easily with it, but it doesn't work that well for multiplication and division. So I'll go over that real quick. In a 10 base, this is your ones column. Here, this is your tens column. This is your hundreds column. This is your thousands column. So this would be 1. This would be 2, and so on, right? There would actually be 11 dots here. And so if I wanted to add up a number, I would go 5 plus 2, and you would see that it's 7. If I wanted to add up a bigger number, let's just say I wanted to add 7 plus 3. I would do like that, and I would first of all take these 2 rocks here, and I would move them over here like that, and like that. But basically, the whole number would come to 10. So I would just end up moving my rock right there. Now, if this rock right here equals 2, and this rock right here equals 5, then that's 7. And so if I had this rock right here equals 3, then I wouldn't actually need to fill up this whole area. But if I did, this rock equals 5, so I would have to fill up all these here like that, and that would be 5, and then I would still need 2 more, so I would put a rock here and a rock here, and then I would need 3 more, so that rock would stay there, that rock would stay there, and I would have another rock there, and so you have 10 rocks there. And then when this whole row gets filled up, I would move that up there. One dot here equals 10. So I have my calculation, and you might think, well, that sounds like a good way to use the YUPANA, but it isn't unless you try to multiply, which is extremely difficult to do. And I'm not going to go over trying to multiply when you're using it as a base 10. So I'll go and explain how I was explaining it before, where it's a base 40. Now, if you remember correctly, this dot here equals 1, this dot equals 2, this dot equals 2, the entire box equals 4, this dot equals 3, 3, 3, so the entire box equals 9, 5, 5, 5, 5, 5, 25. So each dot equals the amount of dots that there is in that box. So this row here is 40. That's called a 40 base because each of these dots here equals, well, this dot equals 40, and then it doubles. This is 80, this is 80. So both dots together in this box, the whole box equals 160. 120, 120, 120. So the whole box equals 360. 200, 200, 200, 200, and 200. So the whole entire box equals 1,000. Okay, so also I think I mentioned that it's on a it's binary, meaning that when a dot has a rock on it, that equals that amount. When there's no rock on it, it doesn't equal that amount. It equals 0. I've also heard that, and I don't know how it works yet, but that also having an empty dot with no rock on it is subtracted that amount. and that when there is a rock, it's to add that amount, and somehow there's no zero, there's no in between. And so that would be some sort of a different math logic that I don't understand yet. If I do figure it out, I'll make a video explaining it. But as it is right now, the only thing I understand about it is that a rock on a dot equals that amount. If it's not there, it's zero. So that rock right there, that this number I'm representing right now is 80. Okay. If I put a rock here, it's going to add 40 because this dot is 40. So this is going to represent 120. So 80 plus 40, 120, is equal to this right here. So you can see some simple addition going on there. In the same way you do the same thing down here. That these two rocks together here, a 2 and a 1, is going to be equal to one rock there. So whatever calculations you can carry on down here, all you do is multiply it by 40. So you're instantly working in far bigger numbers when you're doing it here. So whatever works here works up here. Okay, each dot in this row, this is 1600. This is 3200. This is 3200. And so the whole box is 6400. I think I'm right about that. I didn't write it down in the boxes for this video because it just makes it more convoluted when you write all these little numbers in there. So you're supposed to remember this. Again, it is based on the Pythagorean theorem. And so you'll hear that, not Pythagorean theorem, I'm sorry, the Fibonacci sequence. And you'll hear that the Fibonacci sequence was discovered in Europe in the 1200s by some Italian mathematician in Europe. And that's not true because this is Fibonacci right here. So it's binary Fibonacci. Fibonacci is 1, 2, 3, 5. And so basically in a Fibonacci sequence, every box equals the 2 behind it. So if you were going to count up in a Fibonacci sequence, you add, you're going to add 1 and 1, and it's going to make 2. You're going to add 2 and 1 is going to make 3. You're going to add 3 and 2 is going to make 5. You're going to add 5 and 3 is going to make 8. You're going to add 8 and 5 is going to make 13, and you move your way up with there. Basically, I'm going to try to do some small math problems, and so you can kind of see how it works. Now, another thing is that this is not made for large or for small calculations. Small calculations don't work very well on this unless you're doing it in a base 10. And then if you're using it in a base 10, it only subtraction and addition work well on it. But multiplication and division just don't work. And also small calculations don't work. It's meant for calculating up into the millions. Now, and I'm going to make a video on this, if you want something to do smaller calculations with, this is the Mancala system, and everybody's familiar with that game, and I went over this in a different video. It's similar, except it uses, it's not the Fibonacci sequence. It is binary, so every hole that has a rock in it represents that number, and you do calculations like that, and it works very well for small calculations, but it does not work quite as well for large calculations. If you keep going, this hole right here, this is 1,024, 2,048, 4,096, and you keep going. Basically, you can do huge calculations, but then you have to add up all the holes that have rocks left over in them when you're done with your calculation. So then you're doing addition on top of that. But with this, the numbers all laid out in front of you, and you can go up into the millions and billions easily, very quickly, by just remembering the pattern that worked on the very first row. So again, all of the dots in this row add up to 39, and then when you fill all these up, you're going to move up and put a rock there to represent 40. So let's do some small calculations. this is the kind of thing where you're going to want to already know your basic multiplication tables, whatever you learned in 5th or 4th grade or whatever, 9 times 7, 9 times 5, 9 times 4. You're still going to want to know those because this is not made for doing small problems like that. So we'll do an easy small problem. Okay, I want to do 2 times 5. Okay, so it's pretty easy. I can go here. I know that this equals 5, so all I'm going to do is 2 times 5. And I have 10, so I don't need to really do anything. I already know that. I do want to show you how to count up. So you're going to start at 1, 1 times whatever is its own number. So we're not going to do that. But let's start with 2. Okay, 2 times 1, 2. So we're going to put a rock there. 2 times 2, we're just going to put another one there. 2 times 3, we already know is 6. But there's a pattern in how you're going to count up here. And if you memorize the pattern, you can do it without thinking. So 2 times 1, 2 times 2, 2 times 3. Okay, what does each one of these represent? 3. So when you move up your 2 times 3, you're just going to move these up like that. Okay, 2 times 4, you're going to move one of these up. That's 5 plus 8. Okay, 2 times 5, now you're going to move this up. You see, it's kind of a pattern. 2 times 6 is 12, right? So you're going to have your 10 there. You're going to keep those 2 there. You're going to add 1 here. 5, that's 10. 2, that's 12. 2 times 7 is 14. Now you're going to add another one there. 5, 2, 2. 2 times 8, 16. So you're going to add 2 more. So you can take this down here and you can move that up there. Oh, you have 5, 3. No, that would actually be 15. Yeah, I'm sorry. So you keep that there, that there. 10, and then 3, and then another 3. That's 16. And so you can keep moving up and multiplying. And okay, and I'll do one more. Let's count by 3. Okay, so this is 3. 3 times 1. 3 times 2. 3 times 3. That's 9. 3 times 4. We want to add another 3. But what there's more than one way you can do it. You can put a 2, and you can put a 1. The other way you can do it is you move this rock here, and you make that a 5, and then you're going to put 2 here. So you have 3, that's 6, and you have 5, that's 16, and then 17, 18. Okay, so we're going to add another 3. We could do that. Or we can just move another one there and then put one here. And so eventually the whole thing is going to get filled up, and then you'll move a rock here to symbolize that you've filled all these up. Now, what you're going to know if you're using this is your basic timetables. I'm not going to have to fill all these up doing my small calculations. What is 5 times 8? 5 times 8 is 40. So if I have a rock here and I want to go 5 times 8, oh my, and I'm not going to take and fill all these little dots up and then take them all off and then move them up here. I already know that 5 times 8 is 40, so I don't have to think about it. I'm just going to move it up there. But what if it's 5 times 9? Let's take 5 times 9. Well, I already know 5 times 8 is 40, so I'm going to move my rock there. I want to do, and I know that if there's going to be one more 5, so I'm just going to leave a rock in there. Okay. What if it's 5 times 7? Well, I'm going to be 5 dots short of moving my rock up here. So I'm going to know that all these little holes here are going to be filled up except for one. And so I'm not going to use this bottom row to do these small calculations. So what I want to do is a bigger calculation. So let's just start by multiplying something by 40. Okay. And it's super easy because obviously, as you already guessed, you're just going to move whatever you have down here up one. So I have 7 here, I have my 5, and I have my 2, and I want to multiply that 7, I want to multiply it by 40. So I just instantly scoot them up there. And the number I have here is 200 plus 80, 280. So I know that 7 times 40 is 280. So there's no thought that goes into it. And that's why I'm saying when you're trying to multiply small numbers down here, it gets kind of convoluted and hard to use. It's not meant for that. It's meant for doing huge numbers. So I guess the Incas were doing astronomy or astrology or whatever they were doing with this, and they, when you do that, you, just like the Mayans, you have to calculate huge vast quantities of numbers to do your geometry and figure out where planets are and stuff like that, whatever else they did with it. And so let's say I want to do 7 times 41. Well, that's obvious. I just moved those up there. I have my 280, and then I'm going to put another 7 right there. So I have multiplied by 40, and I still have my 7 multiplied by 1 there. I'm going to do 7 multiplied by 42. We'll start off with our 7, and I want to multiply it by 42. Okay, so I do my first here. I multiply by 40, and then I also multiply by 2, which means I'm going to take this 7. All I'm going to do is put another rock there and another rock there. So I know I have my 280, 200 here, 80 here. I have 10 here, and I have 4 here. So I know that it's 280 plus 10, so it's 294. Okay, and if I want to multiply 43 by 7, I'm going to do 7. I'm going to do my 40. Then I'm going to do my 3. So that means I'm going to have, there's my 7. And then I'm going to multiply it by 1 more. And then I'm going to multiply it again, which is going to be a little different. So I'm going to change the configuration here. I need to get another 7 on here. So this number here represents 14 because 7 times 2 is 14. But I already know, I'm not going to do a bunch of moving the rocks around to count and figure out what it is. I already know it's 21, as anyone who ever used this is. You're not going to get away with somehow cheating and not knowing your basic multiplication tables, okay? And you won't be able to do math at all with any instrument that way unless you have a calculator. And so I already know that 7 times 3 is 21, right? And so I already multiplied my 7 by 40. Now I'm going to multiply my 7 by 3. I know that this whole box here equals 25. Well, it's too big, so I can't use it. But I know that each of these dots equals 5, so I know that I'm going to fill all those up, and it's going to make 20. And then I'm going to have a 1 right there. So then I'm going to look at, it's 280 right here, 280, and then 20, right? The box is 25, but not, the one dot is not full. So this is 20 and then 21. So I'm going to add the 21 to the 280, right? So it's going to be 301. I know the answer. 7 times 43 is going to be 301. So basically, you would just take this and if you're multiplying, let's just say instead of multiplying, you're multiplying 7 by 40, you want to multiply a larger number, you're just going to take and you're going to work from up here. So we'll take the same configuration that I used at first, where I'll show you I was multiplying 7 by 40. Okay, so the fact that there's a rock right here simply means that I'm going to imitate what's up here. Okay, so because I have 2 rocks down here, but I have 1 above it, I just have to imitate that, right? We're going to know that I'm imitating the fact that there's 1 up here and I'm moving them up 1, right? But let's see what configuration we get if instead of doing it that way, we start by moving these 2 rocks up here, okay? We already know what that number was, right? 280. So what down here is 7, up here is going to mean 280. So I want to multiply 280 by, I want to multiply it 40 times. What am I going to be multiplying it by? To multiply 280 40 times, I'm going to put that up there, okay? And so I'm going to move up 1 and up 1. I'm multiplying it 40 times again. But this rock here is 1600. It equals 1600, like I explained earlier. If I had my 2 rocks down here and I have 7 down here and I want to multiply 7 by 1600, I'm going to move them up here like that. So this dot here represents 4800. This dot here represents 8000. And we add those together, we get 12,800. So it might seem like a weird way to arrange all these numbers for this to mean 8,000, for this to mean 4,800 and so on, but they weren't using the same decimal system, or they at least weren't using it the same way we are. They have some Andean languages have the decimal system written into their language, and some of them, I think they pretty much all do, but they did not use the decimal system to make large calculations, which is another thing, is that in modern school they don't teach people anything but the decimal system. However, there's a lot of cases in where it would be better to use like the dozenal system, where you're counting by 12s. If you're doing fractions, the dozenal system's way better than the decimal system. There's no reason to use the decimal system. And it appears that the Incas have this because they were able to use more than one counting base to do their calculations with. In the next video, I want to do some more calculations on this that are bigger, and I'm going to write out the meaning, because even I kind of forget what each of these dots mean because it's a little confusing. I have to wrap my brain around it. So I want to write the values of each dot down on the dot, and then the values of the entire box, and then also make a setup where you can count forward, where you basically can count from this direction, where this dot is 1, so this is 2, so all these added up is 3. This is another 2, so all these added up is 4. Now this is 3 more, so all these added up is going to be 7, or I'm sorry, 5. So this is going to be 8. Add 3 more, that's going to be 11. Add 3 more, it's going to be 14. But you can also count from this way. So there's what I do is I'm not usually going to put all of the rocks here. So there's a whole bunch of rocks piled up on this, because when you're adding up, the whole thing's going to get filled with rocks, and it's kind of too convoluted. Unless you make a YUPANA carved where there's dips, like holes, and you have different colored rocks. You'd have one color of rocks to represent your multiplicator, I think they call it, the number you're multiplying, and then the number that you're multiplying with, and then the sum that you've already created. So you can do it that way too. You have little holes here like dips. Then you have different colored rocks that represent a different aspect of your calculation. And so you're just moving the rocks back and forth like that. And you can do it that way. It's a little easier, and that's how the Mancala system is used. When you play Mancala, there's a board with holes in it, and you're moving the rocks back and forth. And so whatever you're doing, like let's just say you want to represent 5 times 2, right? So you're going to have a 1 here and 1 here, and it's going to be 5. And in order to multiply the 2 by 5, you're going to take your rock and you're just going to move them forward, right? You're going to actually move it forward 1 space to multiply by 2. If you want to multiply 1 by 2, you just move forward 1. This is incorrectly marked here because I made this Mancala here to represent an octal system of counting, because it's easier to add and subtract. And so this, in the decimal system, we would call this 8. We would write it out like that. This would be 16. This would be 32. But in an octal counting system, an 8 is written out like a 10, a 16 is written out like a 20, and a 32 is written out like a 40. And it's easier to add and subtract that way. And that's the one fault of the Mancala system with the trying to use the decimal system with it, is you get these funny numbers that are a little harder to add up. 256, 512. That's harder to add up than when you just look at 100, 400, 1000. So I am sure that whoever invented this was using an octal system, just like I'm sure that whoever invented the YUPANA was using a 40 base system. So basically, in a way, you can use the YUPANA the same way. Now, in order to do that, you actually need to physically make a YUPANA that has holes, similar to the Mancala has holes, because you can move your rocks back and forth in the same way you do on the Mancala. It's the same exact thing. There's really not much difference between the two. So that's the end of this video, and pretty soon I'll try to make another video. This video is just to explain the basis of this counting system, and it's pretty amazing, and it's actually pretty simple.